So let's look at initial conditions as special forcing functions, or really special forcing distributions. And the main point is not to understand much more about initial conditions so much as to understand more about distributions. Although it's kind of a cool way to think about initial conditions. I really like it, and I don't usually see it emphasized in introductory texts that talk about differential equations and distributions. So we've got a mass spring system, and I want to talk about three different ways that basically are equivalent to talk about them mathematically, and one of them using distributions instead of initial conditions. So this typical way you'll see this is we only consider t greater than or equal to 0. Like that's all our whole universe is the right half of the real line. And it's using functions exclusively, no distributions. And it's the differential equation is my double prime plus m omega squared y equals 0, y of 0 equals 0, and y prime of 0 equals v naught. And honestly, if this is our entire universe, this is a little bit of a weird statement. It makes more sense to say like the right-hand derivative of y. So let's say y prime of like 0 plus equals v naught. Okay, but that's a bit of a technicality there. Okay. But I do want to extend it to the whole real line because that's where we've been using our distribution. So an intermediate step is we're going to go to the whole real line, same differential equation, but we're going to say that actually is true everywhere but at t equals 0 where something weird happens. Okay, and at t equals 0, y of 0 is supposed to equal to 0. Okay, and up to in the past, leading up to there from the left-hand derivative of this guy is supposed to be 0. And not surprisingly, if you kind of extrapolate that backwards in the past, it means, okay, nothing was happening back there. But then suddenly the right-hand derivative is v naught, and that's, let's say, greater than 0, just to be definite, but let's say non-zero anyway. Okay, and so it suddenly starts moving. Now, I find that a little bit weird. Why did it suddenly start moving? That's kind of a weird thing. Something weird happened here, and this is sort of an artificial way to say that. Okay. So this is one of the things that's given in the handout with number 2. But then, of course, the answer for number 1. How would you accomplish this? What could you imagine that physically happened to the system if it really was transitioning from doing nothing to suddenly doing something? Well, this is exactly hitting it with a hammer. This is what we've been talking about as our fundamental problem the whole time. You hit the thing with a hammer. And instead of artificially just saying, okay, the velocity changed to v naught, what we're going to say is, well, suppose that hammer delivered a momentum of j, then taking that and imparting momentum of j into a mass m is going to give it a velocity v naught. Okay, so as long as we have this equation relating how much momentum the hammer transfers, how much impulse it gives it, and the velocity, then we should be able to recast this in a third version, which is that it's not homogeneous in terms of the equation anymore. We've got a j delta over here, okay? And that's why it actually went from doing nothing to suddenly doing something. I tend to like that better. Now, we still have to say, in some way, it started out by doing nothing. So we could really pick any point here at t less than 0 and just say that the position and the velocity were 0 there. It's kind of slicker, though. It's not super important to just say that at minus infinity, the position and the velocity were 0. And of course, where this just means, it's a nice notation, just slightly faster for the limit as t goes to minus infinity of y of t, and similarly for y prime. Okay, so we really already know the answer to this question. Is it really true that these are all equivalent? Well, one way to see that they're all equivalent is that y of t equals h of t times j over m omega sine omega t. Solves all these problems. It's very easy to show that it solves the first two versions. The first one is just exactly the standard differential equations variation that this solves that particular initial value problem. The second one is only slightly different. And this is what we've been doing for the last few handouts, a few videos. So I'm not going to go over the details again. Okay, but I wanted to just sort of show that there's this equivalence between those points of view. Okay, so now let's just make it a little bit more general. Okay, if you have, so this is number 3. How much room do I have? Yeah, good. Okay, so we haven't been using the ability to have a damping term much, mainly because I just want to be able to write down the solutions explicitly without have them being messy. But let's say we actually have a damped spring now, and suppose it has a forcing term, okay, and I'm going to write it in the same way. This is sort of the generalization of version 2 that I was just showing. It's always existing for all time. Everywhere but at maybe some weird time t called t equals 0, it's got some forcing going on, some normal forcing. So this is just an ordinary function for now. It could be a distribution eventually, but let's just say it's an ordinary function. Okay. And the forcing, whatever it was doing before temp equals 0, there was nothing. It wasn't trying to do anything. The forcing wasn't trying to make it do anything. Okay. Excuse me. But after t greater than 0, after t equals 0 rather, anything's open in terms of the forcing. Okay. Okay, we need to make it more explicit. It happens to be at equilibrium at temp equals 0, and it comes in there not moving, and then comes out of there moving at v naught, which is j over m. Okay. The claim is that this guy, whatever the solution to this guy, is the same solution to, okay, instead of putting this in there, you can just add it to, and here I decided to write it in terms of v naught instead of j. No big deal. Okay, the j is mv naught, right? J is mv naught. You can think about it in terms of initial velocity or initial momentum. No big deal. Okay, and I still need to say that nothing was happening in the past, and we'll just switch to this way of saying nothing was happening in the past. Okay. All right. So what the question asks is, suppose you have the function that satisfies this. This is kind of the ordinary differential equations formulation of this with a particular initial velocity and no initial position. Does it actually solve this? It's good practice with working with how distributions work when they come from functions. Okay, so let me at least leave that stuff. Okay, and we just got to actually take it on a test function. Okay, first of all, it should be clear that this alternate way of saying what was happening in the past, is definitely satisfied. Okay, a solution to this where the forcing was not happening before t equals 0, and the position and the velocity coming into t equals 0 are 0, it's always been 0. Okay, so we just need to show that it satisfies this plus the mv naught delta. So we're going to take y, and we're going to apply the left-hand side. We're going to look at the left-hand side of this guy. Well, that's okay. And we're going to apply that to a test function. And we just want to see that it is this guy when we apply the test function. Okay, so by the definition of what it means to take these guys and add them and scalar multiply them, this is just my double prime, and what it means to take the derivatives. We'll go ahead and do that. Remember, there's 2 minus signs, so they cancel out. But here, that turns into a minus. And here it's just ky on phi. Okay, so we'll write those out in terms of integrals. M integral, and they're, I need to actually put the limits in explicitly because a lot of them are going to change to zeros in a minute. Okay, y of t, phi double prime of t, dt minus c. So I'm just expanding out the definition of what those brackets mean. Ooh, and it's going to not fit. And that's just y of t, phi of t. So it's just going to be playing with, like we've seen a little bit before, playing with integration by parts and boundary terms. So the first thing is that y of t, that the ordinary solution to this guy remember we're assuming it's a solution in the ordinary sense, like that, it's 0 until t equals 0. Okay, so this guy, I'm going to do a little changing in place, cheat a little bit. Okay, those just changed to 0. That's the first thing. Okay, and now I'm going to do an integration by parts on here and an integration by parts on here, and I do actually have to rewrite. Okay, so let's see. This is going to be m. Okay, so that's going to be y of t phi 1 derivative of t, phi prime, from 0 to infinity. And then a sign switch, because of integration by parts, how that works, is 0 to infinity, y prime of t, phi prime of t, dt. And then another integration by parts. Now it had a minus c y of t phi of t, no derivative. Okay. And then plus, this switches. And then that's going to be y of, y prime of t, phi of t. And then plus, this guy is just unchanged. Integral 0 to infinity, y of t, phi of t dt. Okay? All right. So now some of this just dies. Anything to do with an infinity limit, you can basically just guarantee it's going to die, because the whole point of, part of the point of how we define test functions with compact support is so that those terms never bother us. So that's going to go away. That's going to go away. Now, y of t, though, also is going to go away at 0, because for this particular version of the problem, we know that y of 0 is equal to 0. So this all dies. Okay, so far, nothing interesting is coming out of the boundary terms. That might be a little suspicious, because usually something interesting shows up in these kinds of problems where you're talking about where 0 was important, because there's something happening at 0, and the v naught has to come out somewhere. It'll come up in the next stage, though. Okay, because we're going to take this guy. We still want to get that derivative back off of phi prime, so we're going to do another integration by parts. So we get minus m, and now y prime of t, phi of t, from 0 to infinity. That's going to give us our key term. And then that turns back to a plus. Okay. And so that's going to be plus m y double prime phi of t, and then a plus c y prime phi of t plus k y of t. Oh, okay. So I'm going to just combine that together. And it's just the ordinary, all this stuff in the ordinary way. And you might be like, well, didn't we start with that? And how is it okay that we end up with this? The key is that this is only from 0 to infinity. And we can just interpret this in the ordinary way from 0 to infinity. We know that something is very nice about this function if I just look from 0 to infinity. Namely, this is 0. That was what's supposed to be special about an ordinary solution to this differential equation on t greater than 0. Okay, and now this, okay, you're going to get another minus sign because evaluation down here carries a minus sign. That guy dies, though, and all we just get is m, aha, y prime at 0 is v naught, and then times phi of 0, and that's exactly what you get if you take mv naught delta and you act on phi. Okay, and so the upshot is that we've just determined that as distributions on all of R, this is, oh, my bad. Oh, my bad. I'm sorry. This I was confusing with a different version. I don't think I have to redo this. This was f of t. Okay, so this is just plus f acting on phi. I can save myself pretty well here. So this is just plus f. I was thinking about the homogeneous version, and I'm even staring at the right notes, and I just didn't look at them very carefully. So this says that it's f plus mv naught delta. Okay. All right. So this is a very common thing where you play with integration by parts and you see the boundary terms coming out in the right way to verify what you want carefully. Okay. So again, the upshot is pretty simple. If you want to, in I think kind of a more physical way, make something go from not moving to moving, you hit it with a hammer. Okay. But that's not the only kind of initial condition we can do. Okay, it was getting kind of long, so let me just set this up, and then we'll go right into it in the next video. What about my double prime. Let's take the c out again. What hopefully you saw there is that the c wasn't super hard to deal with. It comes in a slightly more interesting way in these next problems, but let's start out with it not there, just to simplify. What if you have an initial position and 0 initial velocity? Of course, eventually one could combine it. Oh, 0 initial velocity. One could combine it to y naught and b naught, but I want to just focus on them separately. It's better. Okay. We know how to solve this in the ordinary way, but how do you use distributions to take something that's going nothing, 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 and then suddenly, pow, it's at a non-zero position? That's a little bit weird physically, but it's not actually unphysical if we think about it in the right way, and that'll be the next video.